In drawing structural formulas of organic molecules, we have to highlight each single or double or triple bond explicitly. So for example, molecule of propane, we would write out this way. This is propane. And drawing out all these single bonds is very informative, but after a while, and especially if our molecule is rather big, it gets kind of tedious. And so this structural formula can be condensed into so-called condensed formula by simply taking a given carbon atom with its hydrogens and just drawing it out. So this unit is 1 carbon and 3 hydrogens, and we can write this out as CH3. This is then followed by a CH2 group, and then another CH3 group, and this is our condensed formula. So this is much faster to write out. This can be used not only for molecules which have carbon and hydrogen, but also for those that have other elements. For example, a molecule of methanol, which has oxygen, is quickly condensed into CH3OH, and then in these structures, lone pairs are routinely omitted. Okay. If you have a branched molecule, for example, something that looks like this, we can use this concept of condensed formulas to represent these molecules as well. So here there is a methyl group as a branch in the main chain, and the way we would write this would be CH3, CH2, CH, and the branch, our methyl group, is put into brackets, and then we continue with CH2, CH3. If we want to highlight a certain part of a molecule, we're completely welcome to do so. So if we want to, for example, draw this molecule which has a triple bond in it between 2 carbons, this is most commonly condensed into CH3, C, and then triple bond is actually explicitly drawn out, CH3. This applies for double bonds as well. For example, molecule of acetaldehyde, CH3CHO, also known as CH3COH, comes from this structure. Okay? But guess what? Chemists actually think that even this is a little too hard, and they introduced a completely geometric form of drawing molecules which are called the so-called line angle formulas. In this representation, bonds are represented as lines. Carbon atoms are represented as kinks in these lines or junctions of multiple lines. All heteroatoms, nitrogen, oxygen, chlorine, have to be drawn out. When it comes to hydrogens on carbon, we skip them. Hydrogens on nitrogen, oxygen, etc., draw out. Okay? This looks a little cryptic, but it's much easier to understand on an example where we look at this now condensed formula and try to translate it into this. So there's carbon here. So There's a carbon here, another one here, another one here, another one here. So all the carbon-carbon bonds are represented by these lines, and each kink is one carbon atom. If we had something different, for example, a molecule of an aldehyde, which looks like this, then we would go for a carbon, 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 another one, oxygen, and hydrogen. You see, all the carbon atoms are not drawn out. Actually made a mistake. So there is another carbon here, which is perhaps this molecule. Okay, now this is all correct. If we have something bigger or cyclic, we can draw this as well. So this ketone would simply translate into this little hexagon and oxygen. You will see chemists using these structures very, very often, and it's of crucial importance to learn to manipulate these, because these are especially in drawing complex molecules, the bread and butter of organic chemistry. Now we'll talk just briefly about the so-called molecular formulas. And these are really not nearly as detailed as the classes of formulas we drew before. They simply represent the number of atoms of different kinds. For example, if we have an alcohol such as this propanol, this, in terms of molecular formula, is simply C3H8O. The reason why we studied these in the first place, although they're not very informative, is that they're experimentally obtained numbers. They come from elemental analysis. For example, if we analyze some molecule and obtain the following composition, 64 carbon, 10.41% of hydrogen, and 27.55% of oxygen, then this data can allow us to get to a molecular formula. To do that, we'll simply divide by atomic weight each one of these numbers. And so if we divide this by 12, we'll get 5.17. If we divide this by 1, we'll get 10.41. And if we divide this by 16, we'll get 1.72. Okay? Now, so that means that the formula is C5.17, H 10.41, and O 1.72, but this is not very realistic. So what we often do is then divide by the smallest of the three numbers, or more numbers if you have more. Divide by smallest. And then if you divide it by the number of oxygen, we'll get to a structure which is C3H6O1. Okay? And this can correspond to a number of different structures. For example, we can have something like this, something like this, or a couple of other combinations. And how do we determine which one of these two is the real structure experimentally? Will be the subject of the last half of our course. Not half, but third of our course, we'll talk about spectroscopy. But for now, this is how, from the simple composition of the sample, we can get to at least several choices of a given structural form.